So in this lesson, we're going to be talking about rectangular hyperbole. Normally the way you'd go about this is I would sub in all these x values into my rule, y equals 1 over x, and then based on these values, draw a graph. But instead of doing it that way, I'm just going to immediately draw what this graph looks like. And the reason why I'm doing that is because it's very important. The one thing I want you to walk away with is knowing what these graphs look like. That is very important. So I'm going to do a quick sketch of these. To the best of my ability, my drawing is not the greatest, but there it is. So that's very important. The ability to recognize that y equals 1 over x looks like this. Now, there are two very important things about this graph, and it is the fact that we have asymptotes in it. So we have a vertical asymptote that exists here. It exists at x equals 0, and we have a horizontal asymptote along here, and this is y equals 0. Now, how exactly did I know that I had a vertical asymptote at x equals 0? Well, let's explore this for a minute. How did I know that my vertical asymptote was x equals 0? Let me write out my rule, y equals 1 over x. Y equals 1 over x. What would happen if x were to equal 0? Well, I would be left with y equals 1 over 0, and that's undefined. This doesn't work. The world just breaks down. So that can't be the case. X cannot equal 0, and because x cannot equal 0, that's how we know that our asymptote will be x equals 0. Remembering that an asymptote is a line that a function approaches but never actually touches. So on for infinity, y equals 1 over x will approach x equals 0 and approach y equals 0 but never touch it. Perfect. So that's how we knew about the vertical asymptote. How did I know that my horizontal asymptote was, let me do it in red, was y equals 0? This is still simple, but maybe not as intuitive as this. If I was to write out my equation, y equals 1 over x, let me just let y equal 0. So if I was to have 0 equals 1 over x. Now, what's wrong with this? Let me say it another way. Is there any x value that this could be that I would get an output of 0? 1 divided by what number would get 0? And that number simply doesn't exist. This doesn't make any sense. If this doesn't make any sense to you, let me just do some quick rearranging by timesing both sides by x. So to get 0 times x equals 1. What number could x be that I could times it by 0 and get 1 out? That doesn't work. Any number times 0 will be 0. So that's how we know this doesn't work. So in other words, y cannot equal 0. And that's how I know that's where my horizontal asymptote lives. Perfect. So I've just shown you about how to draw the graph and what my vertical and horizontal asymptotes are. Let's now begin filling in my table of values. So it's telling me to plug in x equals 4 into my rule. So let's remember our rule is 1 over x. So if I was to let x equal 4, I would get 1 over 4. So my y value would simply be 1 over 4. For 3, I plug in 3 into my x pot, it will be 1 over 3. And this continues. 1 over 1 will be 1. You might get a little bit stuck here. This is saying 1 over 0.5. How many times does 0.5 go into 1? It goes in twice. How many times does 0.1 go into 1? It goes in 10 times. And we know that x is undefined. So let me just put an x there. Then the same logic over here. This will be negative 4. This will be negative 3. This will be negative 2. So negative half, sorry. This will be negative 1. This will be negative 2, and this will be negative 10. Perfect. So I've filled in my table of values. I've drawn my graph. Let's now do a bit more exploring. I want to know what happens when x approaches 0 from my positive direction. What's going to happen to y? What will y approach? Let me say that another way. So as x approaches 0, so that's there in the table of values. When x approaches 0, what's going to happen to my y value? So let's look at our table of values. As x approaches 0, y is going 1/4, 1/3, 1/2, 1, 2, 10. It's getting bigger and bigger and bigger. If we were to draw a little arrow showing this, as x is getting closer and closer to 0 from my positive direction, my y values are getting closer and closer and closer to infinity. They're getting bigger and bigger and bigger. So as x approaches 0 from the positive direction, I could say y is approaching infinity. Now what's happening when x approaches 0 from the negative direction? As x approaches 0 from the negative direction, let's look at our table of values. I'm going negative a quarter, negative 1/3, negative a half, negative 1, negative 2, negative 10. So I could say as x approaches 0 from the negative direction, my y values are getting larger and larger negative numbers. So in other words, as x approaches 0 from the negative direction, my y is getting closer and closer to negative infinity. You actually can't get closer to infinity, but you know what I mean. I'm approaching negative infinity. Perfect. Let's do some rubbing out. Here, that. Don't need those anymore. We're now going to look at what happens when x approaches infinity. So I just need to rub these out. So what happens when x approaches infinity? So what happens when x approaches infinity this time? So I'm going in the opposite direction. So this time I'm going this way. As x approaches infinity, what is happening to my y? And you can see it here just by looking at this graph. As x gets bigger and bigger and bigger, this line, I haven't drawn it very well, is getting closer and closer to my asymptote. So I would say that my y is getting closer and closer and closer to my 0 from the positive direction. It's getting closer and closer to 0 from the positive direction. And if we look at our table of values, we find that to be true. I'm going 10, 2, 1, 1/2, 1/3, 1/4. I'm getting smaller and smaller and smaller. I'm approaching 0 from the positive direction. What happens when x approaches negative infinity? So this time on our table of values, I'm approaching negative infinity. And on my graph, it would look like this. I'm going this way. Let's first look at my table of values. I'm going negative 10, negative 2, negative 1, negative half, negative 1/3, negative quarter. It's quite clear again that I'm approaching 0 again, but this time I'm doing so from the negative direction. I'm getting closer and closer to 0, but this time from the negative direction. And you can see this here. As x gets bigger and bigger and bigger, my y is approaching this y equals 0 asymptote. Perfect. So this has been a really in-depth look at what's happening with my rectangular hyperbola y equals 1 over x. We've talked about the vertical and horizontal asymptotes and talked about the fact of how they're approaching either infinity or 0. Perfect. Let's now move on to transforming it. So as you see here, what I've done is, this is kind of our parent rule, what we did above. So y equals 1 over x, I have x equals 0 and y equals 0. And now we have this graph, and this part is familiar. It's the same as what we did before, but now we have this minus 2. So the question is, what is this minus 2 doing? And I actually believe the best way to teach maths is to do it through spoilers. So I'm immediately going to show you. This minus 2 is shifting my horizontal asymptote down to here. So now my horizontal asymptote is y equals negative 2, and my vertical asymptote isn't changed at all. It still remains the same. It is still x equals 0. Now I could draw in my graph. So it's going to look like this. And this will look like this. Okay, so how did I know that my vertical asymptote was the same? So I have 1 over x minus 2. The reason why I knew that my vertical asymptote remained the same is because I still can't have 0 in this as my denominator. 1 over 0 is undefined, and therefore I know that this cannot equal 0. And that's how I knew that my asymptote, nothing has really changed in that regard. But how did I know that my horizontal asymptote had changed? Well, remember from our last example, a situation we do not want to be in is this. Because there is no such value of x that could result in my output being 0. So we don't want that to be the case. Well, that would be the case in this example if y were to equal negative 2. And let me show you why. If y were to equal negative 2, if I was to now do some rearranging, and I would have to plus 2 to both sides, If I was to plus 2 to both sides, this would go away, this would go away. I would end up with 0 on my left-hand side, 1 over x. And this is exactly the situation we don't want to end up in because we know that this doesn't work. So this tells us that our asymptote must be y equals -2. And that's how I figured it out. So this value here is going to shift down, -2. If this were positive, it would go up. So this constant at the end is transforming my graph either up or down. Another important thing we need to realize is I also have an x-intercept here. Oh, let me do that in a different color. I also have an x-intercept, and the way I would find that is go to find x-int let y equals 0. So I would get 0 equals 1 over x minus 2, do some rearranging, and I'd be left with x equals 1/2. So here would be 1/2, 0. That would be my x-intercept. Perfect. Let's now move on to our next graph. So again, in the right-hand corner here, I've kind of put in our parent graph, y equals 1 over x. And now, how is this different from this? How is this different from this? And hopefully you can immediately see that I have this -2 down here. And again, I'm just going to give you the straight spoilers. This -2 in my denominator is going to shift my graph 2 in the right direction. So this is where people sometimes get a little bit stuck. -2 in my denominator will shift it in the positive direction. So don't get stuck by that. And my horizontal asymptote will remain the same. How did I know that my vertical asymptote in this case was changed? Well, let me write out my equation. 1 minus x minus 2. Well, we know that my denominator cannot equal 0. We don't want to be in a situation of this. So in other words, x minus 2 cannot equal 0. I'd do some rearranging. I would bring this -2 on the other side, so plussing 2 to both sides. It's quite clear that my denominator will equal 0 when x equals 2. So that tells me that x cannot equal 2. And obviously don't forget to draw the graph itself. That's how you get the mark. So I'll be there and here. And in terms of knowing that my horizontal asymptote didn't change, it's kind of the same logic as we did before. If y were to equal 0, I would end up in this situation. And we know that this doesn't work. Perfect. And the one other thing that you'd have to recognize is I now have a y-intercept. And I could quickly find this by going to find y-int let x equal 0. So I would get y equals 1 over 0 minus 2, which will be 1 over -2. So this will be 0, -1/2. Perfect. So just then, if we were to zoom out for a second, we talked about transforming it left to right by changing things in the denominator. We talked about transforming up and down by changing the constant here, and we did a deep dive into what y equals 1 over x looks like. Let's now just recap that again by talking about the general features here in this nice looking graph here. So what are the general features of a rectangular hyperbola? So first things first, we have A and B. A and B is here. And these are the vertical and horizontal dilations. And in general, don't matter when we're sketching, so we're not going to spend too much time worrying about that, but you do have to be aware of the fact that these numbers here are going to change how I sketch it. So that's something to be very important about in terms of my x and y intercepts. Let's move on to the next one, which is -c. So this one right here. And this is my vertical asymptote. And the most important thing to remember is that it's actually going to be the opposite sign, and we have to remember to factorize in order to get this value. Next, we're going to talk about my horizontal asymptote, which is going to be my d. D is far easier. It's just going to go up or down based on whether this is positive or negative, and this is going to tell us the value by which we're doing so. And as we go through some more examples, we're going to come across reflections as well. And it is safest to find the x-intercept and the y-intercept. We're going to talk about that in our next examples. Hopefully all this has been useful to you. In the next few examples, we're going to kind of touch upon reflections and seeing how dilations affect us as well. So let's now move on. And for this, all we need to do is find what my asymptotes are from this. So just by looking at it, we should immediately be able to identify what our asymptotes for all these will be. So my first one, I could say, well, my horizontal asymptote will be x equals 5, and my horizontal will be y equals 1 based on this. This one will be x equals -1 and y equals -4. So remembering that this is going to be negative, even though this is positive. Don't get confused by that. For this one, let me do my y first because that's easier. I can immediately see that my y is going to be 4. What will my x be? Well, I know that my denominator cannot equal 0. So the first thing I'm actually going to do is write 3x minus 5 equals 0. I then am going to rearrange to get 5 over 3. So I have now found what my asymptote will be. It will be x equals 5 over 3, and my y asymptote will be y equals 4. Let's move on to our next one. Again, we can see that I don't have any constants that are plussing on the outside, so that means that my y asymptote will be y equals 0, and in terms of my x asymptote, again, we're going to set the denominator equal to 0, and then rearrange to find out that my asymptote will be -1/2. Again, nothing too complicated there. So these are all important skills, being able to recognize just by looking at a graph what my vertical and horizontal asymptotes are. Let's now do some graphing. So here I have this rule right here. So again, the best thing you can do is write out what my asymptotes will be. What will my asymptotes be for this? Well, immediately I can see that if x were to equal 0, the whole thing would be undefined. So my first asymptote will be x equals 0, and I could draw that in if I so chose. Let me do that. It will be x equals 0. And I can see that this -6 is going to shift it down here. Y equals -6. Perfect. And then I would simply draw it in. I'm going to have to zoom out a bit because it will be here. Perfect. So this really shows you the importance of first defining what my asymptotes are, and it's just far easier to graph it after that. We would then have to find out what my x-intercept is. So I would say to find x-int, let y equals 0. So when y equals to 0, I have 2 over x minus 6. I do some rearranging. I'm going to be left with 2 over 6, which is 1/3. So this point right here will be 1/3, 0. Perfect. Let's move on to our next one. Again, the first thing I'm going to do is just clearly lay out what my asymptotes are. Asymptotes. I see this -6, and that tells me that my horizontal one will be -6. Let me draw that in. I'm going to draw it a bit higher this time. Y equals -6. And I can see here that it's going to be shifted to the positive direction for my vertical asymptote. My vertical asymptote will be x equals 2. X equals 2. And then I will draw that in by doing this. There. And this. This time I have an x-intercept and a y-intercept, but let me do the x first. To find x int, let y equal 0. So I'm going to get 0 equals 3 over x minus 2 minus 6. Put 6 on this side, 3 x minus 2. Do some more rearranging. 3 over 6. I'm just doing every step just so we're all on the same page. Plus 2 to this side. Get common denominators. I'm going to be left with 5 on 2. So this will be 5 on 2 and 0. And then I would have to find what my y-intercept is. To find my y-intercept, I'm going to let x equal 0. So let me just really write this out clearly. To find y-intercept, y-int, let x equal 0. So I'm going to get y equals 3 over 0 minus 2 minus 6. I'm going to get y equals 3 over, that will be negative, minus 6. Oopsie daisy. 6. I'm going to have to get common denominators, so I'm going to be left with negative 3 on 2 minus 12 on 2. So I'm going to get negative 15 on 2. There's a lot of working out there, but that will be my final one. It's going to be 0, negative 15 on 2. Perfect, and that's how I draw it. Let's now move on to my next one. Okay, so this is a good one because something is happening right here. What is this negative doing? This negative right here is going to cause a reflection across my x-axis. So this is actually going to change how I'm going to draw my graph. But before we worry about that, let me begin, as I always do, by laying out what my asymptotes will be, and we'll worry about that reflection at the end. So my asymptotes will be, again, x cannot equal 0, because if x were to equal 0, the whole thing would be undefined. And this 2 here tells me that my y is going to be shifted up 2. So it's going to be here. Y equals 2. All right. What is this negative telling me? Well, normally I would draw it like this, wouldn't I? I would draw it like this. But now it's telling me that it's reflected in the y-axis. So let me get purple. So it's reflected across the x-axis. So now this will be reflected across my x-axis. So it will now be here instead of being up here. And again, this will be reflected across my x-axis. So it will now be up here instead of being down there. And I have just drawn it. So this is what it's going to look like. My asymptotes remain unaffected. I just need to remember to reflect it across the x-axis. Perfect. And again, I'm going to have to find my x-intercept again. So to find x-int, let y equal 0. And to do this, I'm going to go 0 equals negative 5 over x plus 2 minus 2 to both sides. Divide both sides by negative to get rid of that. Do some switching around. I'm going to get 5 over 2. So right here will be 5 over 2 and 0. Perfect. Most important part about this is that reflection right here. Let's move on to our next example. Okay, and now hopefully you see here, I have a negative in front of my x. What's that negative in front of my x doing? This is actually quite an interesting example, but again, let's not get freaked out at the beginning. Let's just first figure out what my asymptotes are. What are my asymptotes? So my asymptote will be, let's start with the easy one, y equals negative 2 because of this. What exactly will my asymptote be here? Well, I know that 1 over 1 minus x, my denominator, cannot equal 0. So I'll do some rearranging and I'll be left with, let me do it the long way. I could do it that. So therefore x cannot equal 1. If x were to equal 1 in this situation, I'd get 1 minus 1, which is 0. It doesn't work. So that tells me that my asymptote will be x equals 1. And I could draw that in here. X equals 1, and my y will equal negative 2. So it's going to be down here. Perfect. Now, as I said before, this negative in front of my x is going to cause us some reflection issues. So how exactly is it going to be reflected? Because this negative x means it's going to be reflected across the y-axis. But what we're going to see is that being reflected across the y-axis or reflecting across the x-axis is actually the same situation for rectangular hyperbole. So let me actually write this a different way to really show you how that works. So I have y equals 2 over 1 minus x minus 2. I could actually factor my bottom. I could take out negative 1 and be left with negative 1 plus x minus 2. Oh, don't forget to close the brackets. So now, and then I don't have to write this negative 1. I could just kind of put that out the front. And then a nice way to write that would be like this, minus 2. Let me highlight that because that's my end result. Perfect. So this right here is the same as my question. But what is immediately evident after factoring my bottom is that now I have a reflection, and it's also a little bit easier to see that my vertical asymptote is x equals 1 because we're very accustomed to seeing this on this side of the x. But I'd really just want to show you the fact that when it comes to 1 over x, reflecting across my x or reflecting across my y-axis is actually the same thing. So let me first draw just the normal way we would do this without the reflection. So if it didn't have the reflection, it would look like this. Now, if I was to reflect across my x-axis, if I was to reflect across my y-axis this time, because it is in front of my negative x, if I were to reflect across my x-axis, if I was to reflect this across my y-axis, I would be left with this. And if I was to reflect this across my y-axis, I would be left with this. So as you can see, that's exactly what happened in our last one. Nothing changed. So this obviously need to go away now. So hopefully you can see, if I zoom out, I have to zoom out a bit more. In this question, I reflected across my x-axis and I ended up with this. And in this one, I reflected across my y-axis and this is what happened. As you can see, there was no real difference in terms of my reflecting, and that's very important. So now I would have to figure out what my x-axis is. So I'm going to come here and I'm going to go to find x int, let y equal 0. So I'm going to be left with 0 equals 2, 1 minus x minus 2. I'm going to plus 2 to both sides. I'm actually going to bring this up here and be left with this, in which case I will have this. I'm then going to minus 1 from both sides, and I'm going to be left with that. So x equals 0. Ooh, something interesting is going on here. I'm left with x equals 0 as my x-intercept, which means that I've drawn this part wrong. So this is, oopsie daisy, this is why it's so important to find your x-intercept. This will actually pass through the origin. So this is a really horrible looking graph. It's going to pass through my origin. So that's the real importance of figuring out what your intercepts are before you're sketching it, because it's actually going to affect it. But hopefully that kind of shows you how we go about the process of transforming. We talked about reflections. We talked about reflecting across the x-axis and the y-axis, up, down, everything like that, finding the intercepts, the importance of all that. Hopefully this is useful to you. This is purely supplementary to what we do in class. So this is just perhaps I went over something a bit too fast in class and you just wanted a bit of a recap at home and a bit slower. So hopefully this has all been helpful to you.